Welcome to section 2 of chapter 2 for the AS Chemistry lecture series. Section 2 is going to focus on the evidence of electronic structure. So how do we know that the electronic structure that we're studying it's what it is? And how can we relate some numbers and what is called the ionization energy to that electronic structure? We already spoke about the attraction that electrons have for the nucleus and how that attraction is going to be different depending on the energy level. Now we're going to talk about how we quantify that using something called the ionization energy. Ionization energy is something that we discussed in honors chemistry, but only at a very slight level. We spoke about just the general definition of ionization energy, and that's about it. We can measure the amount of energy related to the creation of a +1 cation. And that amount of energy that it takes to create the +1 cation is what we call the first ionization energy. Now, very important here, we're going to distinguish now between different ionization energies. In honors chemistry, we just talked about ionization energy. But we will now talk about how there are multiple different types of ionization energy. The first ionization energy specifically is what we're going to speak of first, and that is usually symbolized by the letters IE with the subscript 1. The first ionization energy refers to the amount of energy needed to remove 1 mole of electrons from 1 mole of atoms of an element in the gaseous state to form 1 mole of gaseous +1 ions. Now notice how we have this definition highlighted, and that's because this is a very important definition with multiple parts that we need to be aware of. Let's start with the energy needed to remove 1 mole of electrons from 1 mole of atoms. So whenever we speak of numerical definitions, things that are measurements, we have to define a range for the measurement. And in this case, that range is 1 mole. So when we talk about the first ionization energy, we're not talking about removing just 1 electron from an atom. We are talking about removing a whole mole of electrons from 1 mole of atoms, meaning removing 6.02 times 10 to the 23rd electrons from 6.02 times 10 to the 23rd atoms, meaning 1 electron from each atom. The reason we do this is because if we spoke about just removing 1 electron from 1 atom, the amount of energy needed to do that is so small that it wouldn't really be quantifiable to a point that we could study it. So instead of studying just 1 electron being removed, we study a whole mole of electrons being removed from 1 mole of atoms, 1 electron from each atom. And that gives us a number that is much easier to work with and is big enough that we can work with it in a realistic sense. So that's the first part of the definition, the removal of 1 mole of electrons from 1 mole of atoms. The second part of this definition is of an element in the gaseous state. And this is actually very important because if we had to remove 1 mole of electrons from 1 mole of atoms in the liquid state versus the gaseous state, the amount of energy it would take to do that would actually be different. And so we need to specify how many, or the state of matter of that element. Because if I was talking about the first ionization energy and I was talking about the amount of energy it takes to remove those electrons from a gaseous element, but then you were talking about the first ionization energy and in your mind you had the amount of energy needed to remove 1 mole of electrons from 1 mole of atoms in the liquid state, then we would be using the same words but talking about a different number in kilojoules, which is down here, which we'll talk about in a second. But we will be talking about a different number because the number for gas and the number for liquid in this case are 2 different numbers. And so when we do definitions such as this for numerical values, we do need to state a lot of the time the state of matter if it makes a difference, and in this case it does. So first part, 1 mole of electrons from 1 mole of atoms being removed. Second part, the elements have to be in the gaseous state. And then the third part is to form 1 mole of gaseous plus 1 ions. And that just kind of puts together the first two parts, because obviously if the original element was a gas, when we remove that electron, that is going to still be in the gas state, so the gaseous. It's still 1 mole because we remove those electrons from 1 mole of atoms. And then finally, the last part here, the plus 1 ion, that is what happens when we remove 1 electron, right? If we remove an electron from a neutral atom, then that new thing that we have created will have a plus 1 charge because we remove a minus 1 charge from it. So we can see that down here, for example. If we look at calcium, we have calcium in the gas state. If we were to remove 1 electron from this calcium atom in the neutral atom in the gas state, that electron will be represented by an E minus, because that's what we use to represent electrons. But the calcium will now become Ca plus 1 in the gas state still. That plus 1 comes from the fact that we have removed the electron. And that even makes sense mathematically. If we look at the exponents here, the calcium has no exponent, it has no charge, so it's neutral, it's 0. If we look at the product side of this equation, we have Ca plus 1 plus E minus. The minus 1 from the electron and the plus 1 from the calcium cancel each other out, giving the overall products a neutral charge, like the reactants. Charges do need to be balanced out in any chemical equation. And so this equation would only make sense if we had that plus 1 calcium, which is the ion that's created. If in this case, this equation that we're looking at right here, let me make sure that everyone's looking at the right thing. Oops, that is a big square. This right here is this right here is the equation for the first ionization energy. And we can see that here, IE1 is the equation for the first ionization energy of calcium specifically. We have 1 mole, because remember that the coefficients in a chemical formula can either represent 1 atom or 1 mole. So 1 mole of calcium in the gas state, like the definition states, is going to become 1 mole of the calcium plus 1 ion in the gas state. So 1 mole of gaseous plus 1 ion. And the electron, or the 1 mole of electrons that was removed. So we can symbolize that first ionization energy in that equation, and then we can actually assign a number to that because we know how much energy that takes. The first ionization energy, or IE1 of calcium, is 590 kilojoules per mole. And remember, this mole to the negative 1 means per mole, right? Or divided by moles. So kJ mole to the negative 1 is the same as saying, let me write this here, kilojoules divided by moles. Because anything to a negative 1 is 1 over itself. So kJ times moles negative 1 is kJ over mole. Now, why is this the unit that we use for the ionization energy? Well, the kilojoule, or the joule, I'm going to write this out, kilojoule. So the kilo is from the metric system, it just means 1,000. But the joule is a measurement of energy. It's how we measure energy. So kilojoule means 1,000 joules. So 590 kilojoules means 590,000 joules. And that's how we measure energy. And then why is this divided by mole? Because it's per mole of electrons removed. Remember, the definition of first ionization energy is removing 1 mole of electrons from 1 mole of atoms. That's why this is saying that it takes 590 kilojoules of energy to remove 1 mole of electrons from 1 mole of atoms. And that's the first ionization energy. So that's removing that first electron to create the plus 1. Now, this is also should be important to point out. This is also going to be measured under standard conditions. And we talked about standard conditions last year. There is a bit of a tweak that we have to make because last year we learned about STP and RTP, standard temperature and pressure, and room temperature and pressure. Well, we're not going to use standard temperature and pressure anymore. So here, when we say standard conditions, we are actually meaning room temperature and pressure. So forget about STP for now. It's not going to be RTP. So that means 20, oops, that is a big blob. So that means 25 degrees Celsius of temperature and 1 atmosphere or ATM of pressure. So we measure all of this under standard temperature and pressure, or 25 degrees Celsius and 1 atmosphere. Why is this important? Again, these numbers are very sensitive. 590 kilojoules per mole is done at 25 degrees Celsius. If we try to measure this energy at, let's say, 10 degrees Celsius, that number will not be 590. It will be a different number. And so the temperature and pressure in which we measure things is very important. Now, this is the first ionization energy. Like I said earlier, there are successive ionization energies. Why? We can take one electron from an element and make a plus one ion. But Ca plus is actually not a natural stable ion. Ca plus is not the ion of calcium that you learned last year. After all, calcium is a group 2 element. Let me bring up my periodic table here. Calcium being in group 2, I try here. Calcium being in group 2 is an element that naturally forms 2 plus ions, not 1 plus ions. So you might be asking, well, Mr. Pendola, why do we know, or what do we need to know, the first ionization energy of calcium? And that's because, well, to form a 2 plus ion, we first need to remove the first electron and then remove the second electron. And those 2 electrons do not take the same amount of energy to remove. So if we go back here, it takes 590, let's clean this up a little bit. It takes 590 kilojoules of energy to remove the first electron from 1 mole of calcium. Well, for the second electron, what we call the second successive ionization energy or second ionization energy, it takes 1150 kilojoules of energy. The first electron removed from an element is going to require less energy than the second electron removed. And then the second electron requires less energy than the third, so on and so forth. So it is very important to note that there is a pattern with removing electrons from an element. We call these the successive electron energies, which are the energies required to remove the electrons in each step. So removing the first electron, removing the second electron, the third electron, so on and so forth. So removing the first electron makes calcium go from calcium gas to calcium 1 plus gas, plus the electron. And that takes 590 kilojoules per mole of electrons that we remove. Then if we grab that calcium 1 plus that we have already removed the first electron from in the gas state, and we remove yet another mole of electrons, or 1 electron from each one, we get calcium 2 plus in the gas state. And that requires 1150 kilojoules for every mole of electrons we remove. So the second step requires more energy. Now this is the stable ion of calcium, calcium 2 plus. But we could, in theory, with enough energy, go in and remove yet another electron from that calcium 2 plus and make calcium 3 plus. That step would be considered the third ionization energy, the amount of energy needed to remove the third electron, not 3 electrons at once, but the third electron. And that will take 4,940 kilojoules of energy per mole. That's why this step does not happen in nature. That's a lot of energy that it will take. Removing the first 2 electrons already cost this atom a lot of energy. in order to remove those first two electrons, we have to remove, or to use 590 kilojoules per mole for the first electron and 1150 kilojoules per mole for the second electron. That is a total of 0, 4, carry the 1, I had to do the math, 7, 1,740 kilojoules of energy in total. Now notice that I'm not putting kilojoules per mole. I'm just putting kilojoules. Why? Because that's not a mole of electrons that we're removing. Technically, that is 2 moles of electrons that we're removing. But it will take a total of 1,740 kilojoules for every 1 mole of calcium 2 plus ions that we want to make. So I could write it as this: kilojoules per mole -1 of calcium 2 plus. So for every 1 mole of calcium 2 plus ions we want to make, it will take 1,740 kilojoules of energy, because we need to add these two up. This is how much it requires to remove the first electron. This is how much it requires to remove the second electron. Not both, but the second. So in order to figure out how much it requires to take both off, we will have to add both of them up. And this is how we write the equation for the successive ionization energy. An easy way to remember this is that the number of the ionization energy you're doing should be the charge of the ion you have in the products. So notice, this is the first ionization energy, so the ion has a +1 charge. This is the second ionization energy, so the ion has a +2 charge in the products. This is the third ionization energy, so the ion in the products has a 3+ charge, so on and so forth. And that number is going to get larger and larger as we go through this. The larger the ionization energy, the more energy that it requires within the same atom, of course. So let's keep going now, because there is a pattern in this. In successive ionization energies, like I said, the energy needed to remove an electron increases within the same element as we go through. This is because as we remove electrons, the net positive charge in the ion becomes larger. And we can show this. Let's use a very small ion, something like beryllium. So let's say we have an ion or an atom of beryllium. We have B. This is the nucleus. And then we have the first energy level, the second energy level, and pardon my drawings, I know they're horrible, but we have n equals 1 and n equals 2 here. And so in beryllium, because beryllium has 4 electrons in total, we have 2 electrons in the first ionization energy, and then 2 electrons in the second ionization energy. Well, what you have to realize is that beryllium has 4 protons. So in here, in the center, we have 4 protons for beryllium. So the positive charge of beryllium is always going to be +4. Whereas the negative charge for a neutral atom of beryllium is going to be -4, and that's why they are neutral. Well, let's say we do the first ionization energy for beryllium, which, if we look really quick, is 900. So for the first ionization energy of beryllium, so IE1 is 900 kilojoules per mole. What does that refer to? When we refer to IE1 for beryllium, we're referring to this first electron. Oops, I erased the whole energy level. We're referring to this first electron going away. So when we remove that electron, we spend 900 kilojoules of energy, but by removing that electron, we are now dropping to a -3 total charge. Now we only have 3 electrons left. Well, what happens? Because that positive charge is still +4, but the negative charge is only -3, the attraction that these electrons are feeling is now going to be greater. Why? Electrons repel each other, but they are attracted to the nucleus. That is a very delicate balance. The attraction to the nucleus versus the repulsion between the electrons. When we remove an electron by doing the first ionization energy, when we remove that electron, we have lowered our repulsion because now we only have -3 as the negative side. But the positive charge is still the same, it's still +4. So the attraction stays the same, but the repulsion gets lower. Meaning that it's now going to be harder to remove those electrons because they're more attracted and less repelled by each other. More attracted to the nucleus, less repelled by each other. So the second energy level, the second ionization energy for beryllium is 1760. So let's put here, IE2 is 1760. Why is it larger? Simply because the attraction is now greater and the repulsion has gone down. Well, when we get rid of this electron, because the second energy level we always remove electrons from the outside in. When we remove that electron, not only are we removing that electron, we're also removing the whole second energy level. So that repulsion is now even less. That repulsion is now even less. That repulsion is not even -2 anymore. It is now -3 anymore. It is now -2. Not only that, we just got rid of a whole energy level of electrons. And so the repulsion is even lower now. And the attraction is still even higher because it's still +4. Let's look at what happens when now we go to energy, or to the third ionization energy. The third ionization energy of beryllium is 14,850. So you notice, is it not only higher? So 14,000, I said 850, I think. 14,850. Not only is the third ionization energy for beryllium higher, it's astronomically higher. Why? We got rid of a whole layer of electrons. That repulsion has gone down so much, it causes these inner electrons, which are really, 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 really attracted to the nucleus by the +4 charge, to be very hard to remove. These electrons are not going to want to budge. They're like a really strong magnet on a fridge. They don't want to go anywhere. And so that makes these electrons really hard to remove, and therefore it takes a lot of energy to actually remove them. So let's go back to our graphic. So this can be seen here. We can see that there are big jumps in ionization energy whenever we remove a layer of electrons. The larger the positive charge, the greater the attractive force is for the electrons, and the less electrons we have, the less repulsion we get. As a result, the more energy we need to remove the electrons. But we can see that there are gigantic jumps whenever we remove all of the what we call the valence electrons. Remember, to give you a quick crash course, remember that valence electrons are the electrons that are in the outermost energy level. So let me write that down here so we don't forget. Oh, that's too big. The valence electrons in the outermost energy level. So the valence electrons are the electrons that are in the outermost energy level, and they're related to the group number for the representative elements. Oh, let me write that on the bottom. So the valence electrons are the ones that are in the outermost energy level, and we can tell how many valence electrons an electron will, or an element will have, based on its valence shell. So if we go here, electrons on the first energy level have 1 valence electron. Electrons in the second energy level have 2 valence electrons. Electrons in the third energy level have 3 valence electrons. Oh, sorry, in the 13th group. Sorry, I've been saying energy level. Electrons in the first group have 1 valence electron. Elements in the second group have 2 valence electrons. And then it jumps over this middle section, the transition elements. We do not do this for the transition elements. So electron elements in the 13th group have 3 valence electrons. 14th have 4 valence electrons. 15 have 5. 16 have 6. 17 have 7. And the noble gases have 8 valence electrons. So by just looking at the group number, we can tell how many electrons are in the outermost energy level of an element. How many electrons are on the last energy level, or the outermost energy level. And this is helpful because we can actually correlate this to the electrons and their ionization energies. So keep this in mind. I'm gonna put this to the side for now. So if we look at the elements starting with lithium, you see that there's a big jump in ionization energy, and that big jump tells us that we have removed the last electron in the valence shell, and we're now in an inner shell. So, for example, if we go back to beryllium, so let's draw beryllium small in the bottom here. If we go back to beryllium, let me use a different color. If we go back to beryllium, remember beryllium has 2 electrons in the first energy level. And then, let me be nicer with this. We have outer energy level, inner energy level, and then the beryllium. So we have 2 electrons in the inner energy level, 2 electrons in the outer energy level. Well, if we look at beryllium itself here and its ionization energies, the successive ionization energies, we'll notice that beryllium has 4 electrons in total. We remove one of these electrons, and that takes 900 kilojoules of energy. We remove the second one, and that takes 1760 kilojoules of energy. When we remove both of those electrons, you'll notice there are no more electrons on this outer shell. So what happens to that ionization energy? The third ionization energy has a really large jump to 14,850. Why? Because we have gotten rid of an energy shell. And when we get rid of that energy shell, it takes a lot more energy to remove that next electron, the third electron, because it's so much closer to the nucleus. That distance has decreased dramatically from the prior energy level. And so you notice that big jump here. So when we look at elements, if we can identify a big jump between 2 ionization energies, what that jump tells us is the number of valence electrons in the outer shell of that element, and therefore, if it's a representative element, its group number. Because again, the number of valence electrons is related to, or the group number of the element is related to the number of valence electrons. So if we see, for example, that beryllium has a big jump between energy, the second energy, ionization energy, and the third ionization energy, because that big jump is between 2 and 3, we know that there are 2 valence electrons in beryllium. And therefore we know beryllium, which is right here, beryllium, which is right here, is in the second group, because it has 2 valence electrons. So if we look at, for example, nitrogen, we'll see that nitrogen goes from 1400 to 2860, 4580, 7480, 9450, and then it jumps from 9450 all the way up almost 40 or a little more than 40,000 kilojoules to a successive ionization energy 6 is 53,000 300. So because there is a big jump between ionization energy 5 and ionization energy 6, we know that there are 5 valence electrons in nitrogen. And again, that checks out because nitrogen is in the 15th group, giving it 5 valence electrons. So just by looking at the ionization, at the successive ionization energies, we can actually identify what group an element is in, even if we don't know what that element is, because we can identify how many valence electrons it has. And then we can even look at the different layers. If we look at sodium, Na, which has 11, it's element number 11, so it has 11 electrons, we can see that after the removal of one electron, for the next ionization energy, it jumps to 4560. It's a 10-fold jump. So that's one energy level there. So let's get rid of these. That is one energy level that we're jumping there. So there's a jump right here. And then we go through 8 more ionization energies, which are all pretty standard. But then it goes from ionization energy 9 to 10. It goes from 28,900 to 141,000. That's another large jump. And that's because these are different layers. This right here is the outermost layer. This is the middle layer. And this is the lower layer. So these two last electrons are being removed from the first energy level. The 8 electrons here in the middle are being removed from the second energy level. And this first electron is being removed from the third energy level. Because remember, as we move towards the nucleus, it requires more energy to remove electrons. So these electrons up here with a lot of energy needed to be removed, those are first energy level electrons, whereas this one that has very little energy or needs very little energy to be removed is all the way in energy level 3, which is why it requires less energy. So ionization energies can actually give us a lot of information. Now, let's study a little more specifically, what are the factors? We have mentioned a lot of them, but what are the factors that are going to affect these numbers? Not just within the same atom, but in between atoms. Because notice, hydrogen has a first ionization energy of 1310, but lithium has a first ionization energy of 1519. That's less than half. So why does it take more energy to remove the first electron from hydrogen than it does from lithium? And then notice that it keeps increasing from lithium to neon, but then it drops to sodium. Why is that? What factors are affecting this? Let's look at that in the next slide. So there are 3 factors, as the count is telling us here. There are 3 factors that influence ionization energy. 2 of them agree and 1 of them disagrees. So we're going to look at them in this order. The first factor is the size of the nuclear charge. And that's very simply put, how many protons does it have, right? So the size of the nuclear charge is just referring to how many protons does this element have. The distance of the outer electrons from the nucleus. So what this is referring to is actually not just the energy level that the electrons are in, or how many energy levels an atom has, but also the atomic size. Some elements are bigger than others, some atoms are bigger than others, and so how does that size affect the ionization energy? And finally, and this is a new word for y'all, the shielding effect of inner electrons. And we're going to talk about this one probably the most, because it's the one that needs to be explained the most. But what this is referring to is repulsion. Remember that electrons repel each other. So inner electrons are going to repel outer electrons. Electrons are farther towards the inside of an atom, will repel those outside of the outside layers of the atom. And that plays an important part in ionization energy. So let's look at the first factor, nuclear charge. And this is pretty straightforward. The larger the proton number is, and the proton number, remember, tells us the number of protons, also known as the atomic number, the larger the nuclear charge that element has, and that attracts the electrons. Positives and negatives are going to attract each other. So if we have a small positive charge versus a very large positive charge, electrons are going to have a much weaker attraction to the small positive charge than they will for the large one. Electrons are going to be very attracted to larger positive charges. And so what that essentially means is that the more protons an element has, the more the electrons are going to be attracted to the nucleus. The more the electrons are attracted to the nucleus, the more energy it takes to remove them, therefore the larger ionization energy. So essentially, to summarize, as the number of protons goes up, so does the ionization energy, because as the number of protons go up, the more attraction, and that is a very important way of phrasing this that you need to remember, the more attraction there is between protons and electrons. And if there's more attraction between protons and electrons, therefore, more energy is needed to remove them. E is just energy, capital E is energy in chemistry. So the more protons, the more attraction between the protons and the electrons. The more attraction between the protons and electrons, the more energy is needed to remove those electrons. It's pretty straightforward in that sense, even though this is not the only thing that we need to consider. So be very careful. This is about one of three factors. And we can see that general increase if we look at group 2 of the periodic table. Again, group 2 of the periodic table is lithium through neon. Lithium through neon, the atomic numbers go 3, 4, 5, 6, 7, 8, 9, 10. So the number of protons increases. 3 protons in lithium, 4 protons in beryllium, 5 in boron, so on and so forth, until we get a total of 10 in neon. If we look at the ionization energy for that group, we'll notice, other than a few exceptions, which we'll talk about later, we'll notice that in general, the first ionization energy for these elements increases from lithium to neon. And that's because they have more protons. Lithium has 3 protons, beryllium has 4, 5, 6, 7, 8, 9, 10. And so in general, that ionization energy increases because there's more attraction. Now again, this is not the only factor that is to be considered here, which is why we have those decreases, and we'll talk about them later. But in general, it increases because of the number of protons. So let's move on to the next thing that affects our ionization energy, which is the distance of the outer electrons from the nucleus. The more distance between the electrons to the nucleus, the less attraction there is between them. And this is pretty straightforward as well. If you think of a magnet, and you're slowly putting the magnet towards a fridge. As we go from, if we have a fridge here, I'm going to very crudely, draw a fridge. If we have a magnet, and we have it really far away from the fridge, there's very little attraction of that magnet towards the fridge. We move that magnet closer, a little more attraction. Closer, even more attraction. And then when we put it right next to the fridge, that magnet just goes and sticks to the fridge. It has a lot of magnetic attraction. And that's because magnetism is distance dependent. The closer two things that have an opposite charge are, the more magnetic strength there is between them. So it's the same thing with the electrons. The closer the electrons are to a nucleus, because electrons are negative and the nucleus is positive, the more attraction they're going to have. Therefore, the bigger the atom is, the lower the first ionization energy. Because if we have something like lithium, which only has 2 energy levels, then the outer electrons, like this diagram shows here, are very close to that nucleus. And therefore, that electron has a lot of attraction to that nucleus. I'm going to write here large attraction. Oh, that's yellow. Let's change the color. There's going to be a large attraction. I can't spell. And large attraction, therefore, means more energy needed. More energy is going to be needed to remove this electron because it's so close to that nucleus and therefore has a large attraction to it. On the other hand, if we look at potassium, which has 4 energy levels and it's a much larger atom, since that outer electron that we're removing first is so much farther from the nucleus, there's going to be a very weak attraction. Because that electron's farther away from the nucleus. If there's a weak attraction, therefore, less energy is needed. Oops, I can't spell. Less energy is needed to remove that electron. Think about it like watching your children, right? Imagine you're watching your little brother, your little sister. The closer they are to you, the less chances they're going to be kidnapped. The more energy someone's going to have to put into kidnapping your sibling. Whereas if you're playing around and your sibling gets really far away from you, you can't see them anymore, that child is very easy to kidnap. You're going to be in a lot of trouble when you come home and you don't have your sibling with you because it takes less energy for someone to take them. They're very far away from you. It's a weird analogy, but I bet you won't forget this now. But essentially it's the same with electrons. The closer those electrons are to the nucleus, the more attraction, the more of an eye that the nucleus can keep on the electron, and therefore more energy is needed to remove it from it. Whereas if the electron is really far away from that nucleus, the attraction is very weak, and you're going to need a lot less energy to remove that electron because it takes a lot less energy to remove an electron so loosely watched. So in summary, as atomic radius increases, as the distance of the outer electrons to the nucleus increases, the ionization energy decreases. All right. And now let's look at the last of the 3 factors, which is shielding. And shielding is the almost weirdest one, I will say, because it's not something that we are used to thinking about. This is something that's very unique to chemistry. But essentially, since all electrons are negative, right, and that is just a fact, every single electron in an atom is negative, you have to realize they repel each other. Now, electrons in the same shell do repel each other, but very weakly. So if we have electrons in the same shell, let me use a color that's not on here. This electron and this electron are on the same shell, and they have a weak repulsion towards each other. Because they're on the same shell, it's a lateral repulsion, so it's very weak. It's there, but not very strong. Not something that we really need to think about. However, electrons that are inside of that atom, electrons in inner energy levels, like energy level 1 in this case, have a lot of repulsion for the electrons in the outer energy level. Electrons that are inside are going to form almost a shield of negative repulsion to the nucleus for those electrons. So it's a tug of war. The electrons on the outside and even the electrons on the inside are all attracted to the nucleus because of their opposite charges. However, the electrons also repel each other, and electrons in inner energy levels are going to have a very strong repulsion to the outer electrons. That means that these electrons are stuck in a tug of war where they're attracted to the nucleus but repelled by the inner electrons. And so these outer electrons have a form of shielding. Shielding is the ability of the inner shell electrons or inner energy level electrons to reduce the effect of the nuclear charge attraction on outer shell electrons. Meaning that these electrons in the inner layer are acting like a shield for the attraction of the nucleus for those outer electrons. That's why we call it shielding. What does that mean? The more inner layers that there are to an atom, the more shielding there is. The greater the number of inner electron layers, the larger the shielding effect on the outer electrons. So the more of these inner layers we have, the more shielding we have, and the more repulsion these outer electrons feel, and the weaker the attraction to the nucleus, which is going to make them, again, very easy to remove the more inner layers that we have. And so, as general, as the number of energy levels increases, and therefore as the period the element is in increases, then the first ionization energy is going to decrease because of the shielding effect, which is tug of war. Essentially, the more repulsion from inner layers that we have, the more inner layers, then the less attraction these outer electrons feel, and the less energy it takes to remove them. So, we're going to do this. So, for example, let's look at sodium's ionization energies, right? So, using what we learned, we can deduce the following things about sodium. First electrons removed have a low ionization energy, meaning it's far from the nucleus. So, if we look at this, we can actually figure out where all the different electrons are in sodium. This is before I go into that, this is a graph that you're gonna start getting used to looking at, right? You need to start getting used to looking at scatter plots. Is what this is. This is not a line graph. This is a scatter plot of the successive ionization energy of sodium. So we have here the number of electrons removed. So the first ionization energy is represented by this X. Second ionization energy is this one. Fourth, fifth, sixth, so on and so forth. And then the y-axis is the log base 10 ionization energy. So it's the ionization energy. Why is it the log base 10? When we take the log of a number, it makes it a lot easier to work with. Because if we go back and we look at the ionization energies of sodium, we have them right here. The very last ionization energy of sodium is 158,700, whereas the first one is 484. That's a difference of over 158,000 kilojoules. If we were to graph those numbers on the y-axis, this graph will be so large in the y-axis that we would not be able to see any identifying features of this graph. So in order to make the numbers more manageable, we do the log base 10 of those ionization energies. And that is a very normal thing to do whenever we're working with really large data sets. Data sets or data where the lowest number and the highest number are so far apart then when we graph it normally, we wouldn't be able to see anything. So we do a log base 10 in order to do that. Now, if we look at this, we have the first ionization energy for sodium is right here. Then when we look at the second one, there's a big jump here between the first and second ionization energies. So let's mark that. We have here a big jump. Actually, So we have a big jump. Then from ionization energy 2 all the way to ionization energy 9, there's just a slight increase. Not a big jump, but a slight increase. And then from ionization energy 9, these are not very well lined up, to 10, there's another big jump, with 10 and 11 also having a slight increase. So this tells us things. Remember, we said that when there's a big jump, that means we're crossing from one energy level to another. So here we can tell that whenever there's a big jump, that's going to separate energy levels. So we have energy level 1 up here, energy level 2 in the middle, and then energy level 3 down here. Now you might be asking, Mr. Brenda, why isn't this energy level 1? Well, remember, The lower the number the ionization energy is, that means it's farther away. We saw how farther electrons have less attraction because of distance, and electrons that are in higher energy levels have more shielding. And therefore, those two things are going to make it so that we have a lower ionization energy. So the lowest numbers that we start with are the higher energy levels. That also, remember that we remove electrons from the outside in, not from the inside out. Removing electrons is like eating an onion or eating a jawbreaker. You don't eat a jawbreaker from the middle out. You don't eat an onion from the middle out. You eat it from the outside in. So this is energy level 3, then energy level 2, and then energy level 1. We can tell again the division from those big jumps and the number, because the farther inside, or the lower the number of the energy level, the higher its ionization energy will be. The second electron removed has a much higher ionization energy. Again, what changes here? Both distance and shielding change from energy level 3 to 2, because we have gotten rid of energy level 3, so the atom has become smaller, and energy level 3 has shielding from 2 and 1, whereas energy level 2 only has shielding from energy level 1. Now, all of the electrons in energy level 2 have the same amount of shielding, and they're roughly at the same distance. So you can see how the changes are not great. Now, it still increases. Why? Because remember, electrons still have lateral or sideways repulsion. If we go back to that prior drawing that we have, remember that while the shielding refers to the repulsion between these two electrons in different energy levels, this electron and this electron in the same energy level still repel each other a little bit. So when we get rid of one of them, that means that we're getting rid of some repulsion. And so the energy level goes up a little bit because the attraction to the nucleus is slightly bigger. So that increases throughout energy level 2. And then once we get to energy level 3, then there's another once we get to the 8th electron energy level 2, there's another big jump to the first energy level, because again, the first energy level is even closer to the nucleus, shorter distance, and there is no shielding in energy level 1. And that makes them the innermost energy level, and therefore the ones with the highest ionization energy. We can compare this to the actual atom for sodium. So we can see this right here in green. I'm going to highlight them in the proper color. Let me do this one. So the electron in green here is this electron, right here. It's going to be the farthest out and has the most shielding, and therefore that's why it has the lowest ionization energy. The electrons in blue here, let me see if I can do this properly because it's not the easiest thing to do in the world. These electrons here in blue are these electrons right here in the second energy level. Notice, shorter distance than the ones in green, and less shielding because there's only one inner electron. That's why they have a higher energy level than the one in green. And then finally up here in purple, these two electrons are these two electrons right here in energy level 1. They are the closest to the nucleus, and there is no inner energy level beyond that. So there's no shielding whatsoever. And so their ionization energy is really, really, really high. All right. So that's just to show you how this graph of ionization energies relates to the structure of the atom. And this is a relationship. It's a really high level critical thinking type of question, but it is a type of question that you might have to answer on the AICE exam. Speaking of questions, let's do a paper 1 question that's related to this. So let's look at this question. This question gives us a bit of information and then 3 options. The successive ionization energies in kilojoules per mole, and it's always almost going to be in kilojoules per mole, of an element X are given below. So they're not telling you what element this is, right? Because that's what the answer is. They are giving you the ionization, the successive ionization energies. So this is a matter of looking at data and interpreting it, because the question here is, what is X? All right. So we're going to look at this data, and whenever we have successive ionization energies, it's always going to be the same thing. The point, whenever you have a successive ionization energies and they're asking you to analyze the data, is going to be finding that jump and figuring out how many valence electrons it has. Well, if we look at these, and you have to be very careful, because sometimes the jump might not be what you expect, or a jump that looks large is actually not quite that large. So for example, going from 870 to 1800, that might seem like a big jump at first because it's 1,000, but always look at the rest of the energies and just look for the biggest one, not just one that seems big to you. So that's 1,000. 1,800 to 30,000 is 1,200 difference. So see that 1,000 doesn't seem large anymore. 300,000 to 3,600, 600 to 5,800 to 7,000. Again, those are not very large. And then we get here, 7,000 all the way up to 13,200. That's a jump of almost 7,000 compared to the biggest jump before this we had, which was around 1,200. So the big jump here, it's going to happen right here. So if we go back and we number this is the first ionization energy, second, third, fourth, fifth, sixth, and seventh. So if we look at this, we have the big jump happening between the 6th and 7th ionization energies. That means that this element has 6 valence electrons. Remember, if you happen to be 6 and 7, then there are 6 valence electrons, always the one before the jump. So these are 6 valence electrons. So whatever element we have here, whatever X is, has 6 valence electrons. Now, in order to do what we need to do here, we need to look at where these elements are located. So we have AS, ZR, TE, and I. So AS, CR, TE, and I. AS, let me highlight them. Actually, let me highlight them here. AS is, so here's TE, AS, ZR is, where's zirconium? Probably should have highlighted this beforehand. ZR, what was that one? An I think. ZR and I. So here's I. This is not one of them. ZR is... I am very bad at this. Let's just use a little bit of help. Control F. ZR. No results. Oh, here it is. So we have ZR, AS, T, and I. If we look at the valence electrons here, iodine has 7 valence electrons, T has 6, AS has 5, and Cr is a transition metal. Since Cr is a transition metal, technically this only has 2 valence electrons, because the D sublevel, which we'll talk about later, electrons in transition metals don't count. So these all only have 2 valence electrons. So it's 2, 5, 6, and 7. So if we go back to our thing here, we have for ZR, it's only 2 valence electrons. For AS, it's 5. For T, 6. And for I, it's 7. Since we know that our data set tells us that we have 6 valence electrons, then our answer has to be tellurium, because none of the other answer choices have 6 valence electrons. And this is something that you should be doing with paper 1 style questions in Cambridge. You should use your answers to narrow down your choices. Let's say if we weren't sure if the big jump was between 6 and 7 or between 3 and 4. Well, none of the answers are 3 valence electrons, so you could have eliminated that. But not only that, once you figure out how many it is you have, look at all your answer choices. Once you find one that has 6, that's your answer. You don't need to look any further. And so if we look at our answer here, our answer is C, which is tellurium. So this is just one example of many that we're going to do of past Cambridge questions. This one particularly was for paper 1, but we'll look at different styles of questions. That is it for section 2. I'll see you next time when we go over section 3 of this chapter 2.